Okay, so session's being recorded. So last time we talked about polar curves, polar coordinates and curves and polar coordinates from section H.1. And for curves and polar coordinates, of course, you can find a bunch of points, plot the points, and get a feel for how the polar curve is going to be. But I also told you how to graph a polar curve using Desmos. So if you go into Google and type in the search window DESMOS, it's a graphing calculator that can do a lot of nice things. How many actually use Desmos to graph their polar curves from section H.1, or use them to help? Okay, Kahindi did. Okay, and Snega, good, and of course it's in the last recording, the lecture of the recording of the last lecture. You know how to use Desmos, and it's very easy, very easy. So good. And you know, when I took Calculus 2, we didn't have any calculators like graphing calculators or Desmos or internet or anything like that, really. So you know, we had to do it by plotting points and getting a feel for it, intuition, and there's nothing wrong with that. You have some flexibility on how to graph polar curves. But then we also talked then about section H.2, where we found the area of a right-hand side of a region underneath a polar curve. The polar curve was r equals 4 plus 3 times the sine of theta, and we found the area under that polar curve. And actually, let me just see here. Let me just. You have the example copy, but this was the problem that we did. Okay, find the area of the right half of the region enclosed by the polar curve r equals 4 plus 3 times the sine of theta. And of course, we use Desmos to draw the picture of this polar curve, and the shaded region to the right is the area that we're looking for, this area here. And the formula to find, hold on here. One moment. Okay, so the formula to find the area of the polar region was, well, strictly speaking, the formula was equal to the integral from, well, a to b of 1/2 times r squared d theta. So your limits for a and b are angles. Okay, and we learned that this region here starts there, and we look down 90 degrees. So the starting angle was negative 90 degrees. And then the region, the polar curve, kept going all the way up to here, this point. And there, for that point, you're looking up 90 degrees, in the direction of 90 degrees for that radius. And so the ending angle was pi over 2. And so, you know, r was equal to 4 plus 3 sine theta. We square that, and we get this using FOIL, first outer inner last, for multiplying two binomials. And of course, the last class, you took this for granted, this formula. You took this for granted. And I'm going to show you how they get that formula, okay? Anyway, this is the rest of the problem we did in the lecture. So just refer to the previous previous lecture, the recording, to see that. But I just wanted to kind of give you a little refresher of what we did. And man, where's this formula come from here? Okay, so that being said, let me bring up the ebook here. Okay, when they talk about areas and polar coordinates. All right, so how do they get that? Well, they start off by saying that the area of a sector of a circle is 1/2 r squared times theta. So a sector like a circle, if you take like a piece of the circle, like a pie, that's a sector. Okay, so this here, well, hold on here. This is a sector of a circle with an angle theta in radians, of course, but we always go from the degrees to radians, radians to degrees. Hold on. I think there might have been a question. No, we're good? We're good? All right. So, the way I think of this formula, the area of a sector of a circle is 1/2 r squared theta. Think about a full circle. A full circle, what angle would you need to have the sector, your sector, be a full circle? What angle theta would you need for your sector to be a full circle? What angle theta would produce a full circle as a sector? Michael, you're almost right. You're almost right. Not 365 degrees, but 360 degrees. That's right, Candy. And Michael had the right idea. So that equals, no problem, that equals 2 pi. 360 degrees equals 2 pi. Okay, so you're used to the area of a circle. The area of a circle is what? Area of a circle is pi times r squared. Well, if you, in that highlighted area formula there, if you replace theta with 2 pi, then that area of a sector formula works for a circle. Area equals 1/2 r squared times 2 pi, which is pi r squared. And I think intuitively, if you were to look at the area of half a circle, you'd see, oh, that's 1/2 pi r squared. Well, if a half of a circle, an angle of 180 degrees would produce a sector that's a half of a circle. 180 degrees is pi, so if you put pi in for theta, area will equal 1/2 r squared pi, or 1/2 pi r squared for the area of half a circle. So intuitively, when you look at this formula that way, it makes that formula for the area of a circle understandable. And that being said, let's proceed on here. So in figure 2, what they do is they have a polar curve, r equals f of theta. There it is. And the polar curve there starts at theta equals a. That's your starting angle, and then the polar curve ends at theta equals b. And then you're looking for the area of the region inside. So what you can do, it's analogous to what you do when you learned about finding the area underneath a function from a to b. You inscribed rectangles and found the areas of the rectangles and added up those areas and took the limit of the sum of those rectangles, some of those areas, the Riemann sum, and you got an expression for your integral. We can do the same thing here. We can take the area under the polar curve, r equals f of theta. We can take that region and break it up into different little sectors. And each little sector has a starting angle and an ending angle, starting angle and an ending angle. So like the highlighted sector that they're showing there has a starting angle of theta I minus 1 and ending angle theta I. Just like when you learned about areas under functions, you had, you know, a subinterval starting at x sub I minus 1 and ending at x sub I. So you see what we can do, if we want to approximate the area of this polar region R, all we need to do, we can approximate it by adding the areas of all the little sectors, okay, from underneath, or, you know, based on that polar curve, R equals f of theta. And so, and incidentally, the area of one sector of a circle would be approximately delta A, okay, and that's 1/2 f of theta squared delta theta. So, you know, you're used to 1/2, well, the area of a sector of a circle is 1/2 times r squared theta. Well, in our case, the radius of that defines the edge of the sector is defined by r equals f of theta. And the difference in the angles that make up the sector would be delta theta. And of course, then you get a little area of delta A sub I of the ith sub sector, okay, underneath the polar curve. So delta AI is the area of the ith sector underneath the polar curve. But it's just an approximation, because you can see in figure 3, the sector of the circle isn't completely contained, you know. I mean, the only way a sector of a circle would perfectly work is if you had an actual circle. But the sector of the circle will approximate that delta A sub I area better and better if your angles, your delta theta, gets smaller and smaller. And again, this is just analogous to what you learned about, you know, the area underneath the function. I mean, the total approximation of the area would just be the sum of those areas, those areas of the sectors. Okay, and as you let n go to infinity, it's going to get better and better, the approximation, and you get a Riemann sum. As you let n go to infinity, you get a Riemann sum, and that's going to give you then the true area underneath the polar curve from starting angle theta equals A to ending angle theta equals B. And that area is going to be 1/2 times the quantity f of theta squared, d theta. All right, so and incidentally now, so now you have the formula there. Now, I mean, are there any questions now on that formula, how it comes about? All right. All right. Well, all right. And of course, they abbreviate the formula this way by replacing f of theta by r, because it's with the understanding that r equals f of theta. So of course, what we want to do is we want to look at some examples. Okay, and we already saw one example. Let me go to example 1 in the book here. If there are no questions, let me go to example 1 in the book, and let's have a look at that. So here we want to find the area enclosed by one loop of the 4-leaf rows, r equals cosine 2 theta. And they've drawn a picture here of that 4-leaf rows. They want to find the area enclosed by one loop, so they just choose the loop on the right. Okay, and for that loop, that closed loop, you have a beginning angle and an ending angle. Okay, so they're saying that the loop is swept out by a ray that rotates from theta equals -pi/4 to theta equals pi/4. Okay, and do you see how this, in polar coordinates, theta equals a number is a line segment or a line, right? We learned that already. So they're drawing a line or a line segment, theta equals negative pi over 4, and the polar curve, starts there, and it completes its loop at the ending angle of theta equals pi over 4. Okay, so you have to get the beginning and ending angles. And could we sort of mathematically justify why theta, based on the polar curve, r equals cosine 2 theta, what would the radius equal when theta equals negative pi over 4? What's the radius equal to? Go down a little bit, get the whole thing in there. That's right, Colomb, 0. If you put in negative pi over 4, 2 times negative pi over 4 is negative pi over 2. The cosine of negative pi over 2 is 0. So that means that when you're looking in the direction of negative 45 degrees, the radius is 0. And then the radius completes a loop, and you could go to Desmos and see, hey, that makes sense, that loop. But you have to also figure out for what angle of theta is the loop done? Does it has its, you're tracing out the loop. You start at an angle, theta equals negative pi over 4, but then the loop ends at another angle. Now, why did they pick theta equals pi over 4? Why does it end at theta equals pi over 4? Well, what's the radius that polar coordinates, there's always a radius and an angle. When theta equals pi over 4, based on the picture, what's the radius? What's r equal to for that angle? That's right, Colomb, it equals 0. So it makes sense then that your ending angle would be negative pi over 4. Okay, and so are there any questions on that? You have to let me know if you're uncomfortable. Okay, all right. Well, so then the area is going to be the integral from negative pi over 4 to pi over 4 of 1/2 r squared d theta, and r squared is cosine squared of 2 theta. Okay, and now you have to integrate cosine squared of 2 theta, and there's an identity for that. So the cosine squared of x is equal to 1/2 times 1 plus cosine 2x. How many have seen that identity in your trig class when you took trigonometry? That's sort of common, or in pre-calculus maybe? Okay, Kahindi remembers it. Michael remembers it. Good, I was getting kind of worried there. If only, there's a third person remember it. It'd be nice to have 3, but. Uh-oh, Mohammed. All right, well, Mohammed, you're learning something good then, okay? And remember, class, the appendix in the back, the appendix, this whole section on polar coordinates is in your appendix in the back of the book, but there are other things in the back of the book too, like Appendix C has a section on trigonometry if you need to review trigonometry, right? And all right, so the idea is we need to integrate the cosine squared of 2 theta. Well, using this identity here, cosine squared of x, for cosine squared of x, well, x is going to equal 2 theta. So cosine squared of 2 theta would be 1/2 times 1 plus the cosine of 2 times 2 theta, which is 4 theta. And so this is how you get your answer. Then take a look at it. Let me know if you have any questions. Okay, and incidentally, can we get for the area, can we get a negative answer? Or does the answer have to be positive in the context of the polar curves? Would it make sense if we had a negative answer? Yeah, that's right. It's always going to be positive. That's right. That's right, Eric. All right, are there any questions before we move on? Okay, so the next example we're going to do here, we've got another example here. They want you to find the area of the region that lies inside the circle r equals 3 sine theta and outside the cardioid r equals 1 plus sine theta. So here you have two polar curves, and here's a little picture below in figure 5. Okay, and I want to just I want to work really from this example. Okay, I think it'll be fine to work from the example. So, okay, so like we can go into Desmos and we can graph these curves. Does anybody want? I mean, I guess I can. Hold on here. Let me go into Desmos real quick. I'm going to Google Desmos. Okay, and I get the graphing calculator. Doesn't hurt. We'll come back to this. It doesn't hurt to bring it up. That's not it. Hold on. Got it right here. Let me see. Come on. There, that's better. Desmos. Okay, so what I'm going to do is I'm going to, one moment here, I'm going to type in r equals 3 times the sine of theta, and I'm actually going to type theta. There it is. Right, and I'm going to type also r equals 1 plus the sine of theta. Okay, and I can see here there's a lot of real estate, a lot of space that, I mean, I'd kind of like to, well, I want to change the window a little bit here. So on the, let me see here, one moment. On the x-axis, let me just go from -3 to +3. And on the y-axis, let me see here, let me go from like, I don't know, -5, no. Let me go from, maybe this wasn't a good idea. I liked the how it looked before. That's okay. All right, that's nice. Okay, so all right. Are there any questions so far? Are you following with me in on your computer in Desmos? You want me to wait for a minute? Who wants to follow along? Open up Desmos on their computer and try this with me. All right, so according to the left here, the red graph is r equals 3 sine theta. I like that on the left. You can see that they have like, you know, red and blue. The red graph is r equals, the circle r equals 3 sine theta. And the blue graph is the cardioid, r equals 1 plus sine theta. What's cardio stand for, by the way? Cardio. What does that stand for? It's a yeah, the heart. It stands for the heart, and that blue graph looks like the heart. And we want the area of the region that lies inside the red circle, but outside the cardioid. So what I want to do is I want to shade. Well, I mean, I know what I'm looking for. And actually, class, I have a question for you. Well, I mean, I was just debating. I just thought I might try. Can we shade this in Desmos? Can we shade that area? I mean, of course, we could draw it like on the final exam. I would want, on a problem like this, I would want you to take this graph, draw it on your paper, and shade in the appropriate area. And that's helpful for you too. But in Desmos, let me just see here if there's a way to do shading. I'm just curious. Let me see here. And if not, you know, we won't be, let's see. Look at the little wrench here. They have a lot of features, but I don't want to do. Tell you what, I won't take time now for it. If I, you know, I'll investigate a little bit, and if I find something, I'll let you know. Okay. If any of you find something, let the class know. Let's see. Colomb has an interesting comment. If you change to an inequality, you can, on a graphing calculator. Yeah, I understand. If you have an inequality, it can do shading on like a graphing calculator. That might be the answer. I'll think about that, Colomb. Thank you. All right. Well, so we have the graph and we know what the shading is going to be. All right. Are there any questions before I go back to the textbook? All right, let me go back here, back to our book. Sorry. How many of you love Desmos? I know some of you love Desmos, right? Okay, do we have a con? Okay, Felicity says it helps. I agree. And here's clearly the shaded region that we're looking for. This is the shaded region that we're looking for. Right here. So the blue area is inside the circle, but it's outside the cardioid. And they're saying that the points of intersection of this blue, well, this blue region begins at theta equals pi over 6 and ends at theta equals 5 pi over 6. Now, how are they getting that? Those angles appear to be points of intersection between the two polar curves, right? So how would we find those two angles? theta equals pi over 6 in the first quadrant, and theta equals 5 pi over 6 in the second quadrant. How would we find those two angles? Well, the radius doesn't the radius doesn't, and I appreciate your volunteering here, Michael. The radius doesn't equal 0 for theta equals pi over 6 and 5 pi over 6. The polar curves are the radius is positive. Well, you know, it goes out. Like, if the radius were 0, the point would be at the origin. Now, you might be looking in the direction of 30 degrees, but your point would be at the origin if the radius were 0. And at theta equals pi over 6 and theta equals 5 pi over 6, you know, 30 degrees and 150 degrees, the points of intersection, the radius is positive. So how can I confirm that those angles are right? They just sort of, okay, that's where they intersect each other. That's right. So what we'll do, I'll go to the blackboard, the whiteboard real quick here. All we need to do here is set 3, try to do this as good as I can, set the polar curves equal to each other. Okay, and solve for theta. So what would I do here? I have 3 sine theta equals 1 plus sine theta. What can I do to both sides of the equation? I can subtract sine theta from both sides. You should have seen a little of this in trigonometry. And so on the left side, you have 2 times the sine of theta equals 1, right? So that means the sine of theta is equal to 1/2. Sine of theta equals 1/2. And if I draw an XY axis here, what quadrants is the sign positive? For what quadrants? There are 4 quadrants. Which quadrants is the sign positive in? That's right. Good, Michael. The first and the second quadrants. Okay, so the sine of theta is equal to 1/2. All right, the sine. So I'm gonna draw a triangle here. I guess I'll try to use this here. Right triangle, of course. And I'm going to put a 1 there. And I'm going to put a 2 here. Sine of theta is opposite over adjacent. This side here has to be √3, right? And we have a 30, 60, 90 degree triangle. So this angle here is equal to 30 degrees, or pi over 6. Okay, that's one of your intersection point. That's has to be one of the angles. Now, the other angle, the sign is also positive in the second quadrant. Okay, so I'll draw another right triangle here. Trying to draw it. I think it's having trouble keeping up with me. Come on. There we go. All right, we'll have to do it the old-fashioned way. There we go. And I have a 1 here and a 2 here. This, of course, is negative root 3, but that's not really what we care about. The reference angle here is 30 degrees, but that means then that this angle here would equal, it would equal 5 pi over 6. Because 180 degrees minus 30 degrees that's a minus there. Man, we can do better than that, class. That's 150 degrees. Which is 5 pi over 6. All right, so you're going to be doing a lot of that with these problems. You have to find the points of intersection. Are there any questions? Is that a nice trig review for you? Good, Candy. Great. That's great. Tina likes that, and we'll get back to the book then, and we'll continue. So the book just sort of says, hey, you know, pi over 6 and 5 pi over 6 are your angles, but you know they leave out this. This is theta, right? Equals. So you have 2 thetas. They leave out this piece of information here. Okay. May I go back to the book? Is anybody still copying? Or Tina says F parentheses Y. I'm still learning abbreviations. TC means take care, right? TC? Is that? Oh, that's a thumbs up? Okay, Candy. Oh, okay, okay, I got you, I got you. All right, well, let's go back to the book then. All right, back to the book. That's not the book, hold on. Okay, so now what they do is they say, okay, the desired area, okay, and remember what we're doing here. We're finding the area of the region that lies inside the circle and outside the cardioid. And they're saying that we can find that area of the region by subtracting one area from another area. So the first area here, the first area is the area that the 1/2 times the integral of pi over 6 to 5 pi over 6 of 3 times sine quantity, 3 times sine theta quantity squared d theta. That's the area underneath the circle from 30 to 150 degrees. If then you subtract the second area from that area, the second area is the area underneath the cardioid, okay, from 30 degrees to 150 degrees. If you subtract those areas, that's going to be what you need to do. That's what you need to do. Okay, so let me just see here. Let me try something here, class. One moment. I'm going to copy this image here. I'm going to copy this image. And I want to go back into the whiteboard. I want to try something here. See if this will work. I wanted to paste the image in there. All right, I'll tell you what. Let me continue the work here. One moment, class. Let me upload the, I have it worked out on paper, okay? And I wanted to just see if we could maybe do it without that this time, but I think you need a few details. So I'm going to go ahead and bring it up here. Just give me a moment. Gosh, hold on. What is this? Hold on. It's the wrong thing. All right, I have a better idea. One moment. I have a better idea. Let me go back to the book. One moment. Let's be considerate. We'll stay with the book. Does this make sense? Does this make sense that this subtraction of these areas? Does it make sense the subtraction of those areas would give you the blue area? That's really what I'm trying to see if you're comfortable with. Snega's comfortable with it. Colombe's comfortable with it. Michael's okay with it. what you're doing, let me just see here, is when you're subtracting the areas, okay, the first area, hold on one moment. The first area yeah, that's right, Michael. When you did, hold on. Man alive, this is, so when they subtract the areas, what they're doing, hold on, that ain't gonna work. Try it again. Gotta have quality, gotta have quality. Okay, let me go here. It's like you're taking this area here, okay, where R equals 3 times the sine of theta. And in terms of angles, because I think I can be, this is the theta equals pi over 6 angle. Maybe I'll put that in red. This is theta equals pi over 6, like from there to there. And this is theta equals 5 pi over 6. Okay. Okay, one moment. All right, and then they are subtracting yeah. They're subtracting like, well, that isn't exactly right. Hold on. They're subtracting this. And the difference is going to equal that. This here, by the way, is from the second pictures from this part here, the radius part that defines the polar curve. That's the 1 plus sine theta part. And then you get this blue shaded part, which if you go to figure 5 in the textbook for appendix H.2, that's exactly what you have. Okay, that's exactly what you have. All right, and then you know the first integral here, right, was 1/2. Boy, this is where remote teaching takes more time. The first integral from, this is example 2 we were covering. First integral goes from pi over 6 to 5 pi over 6 of 3 times, separate this, 3 times sine of theta squared d theta. And then the second integral goes from pi over 6 to 5 pi over 6, where you have 1 plus, we're subtracting here, 1 plus sine theta squared. Does this help you to see why we subtract those two integrals? Is this was this helpful? This little whiteboard thing I'm doing here to accompany the example. Okay, Michael finds it helpful. Is anybody else? I mean, okay, Kahindi finds it helpful. Rodrigo, good, good. See, I'm thinking about these problems, and I'm thinking about the parts that you're going to have difficulty with. Thank you, Eric. Eric does too. I'm thinking about the parts that you're going to have difficulty with. And, you know, this is where students have difficulty. They have no problem drawing the polar curves, but figuring out how to get the area of the region is what's difficult sometimes. And you can see that if you take this area here and, you know, take that area and subtract this area, you're going to get this area. And that's the area that they show in figure 5 in the textbook from section H.2. And if you're comfortable with that, let's finish up the problem so you can have some time to work on your H.2 exercises while while our class is while we have class, right? And I'm here to help you. Okay, so that being said, then let's go back to the book here. Okay, so now it's time to evaluate all this. And what they do is, of course, for the second integral, 1 plus sine theta, they have to, that's squared. So that's 1 plus sine theta times 1 plus sine theta. So the integral, the second integral here, becomes 1 plus 2, the integram becomes 1 plus 2 sine theta plus sine squared theta. But they also do something else. They notice that the region is symmetric about theta equals 90 degrees. Okay, if you look in figure 5, the region, there's symmetry. The right half, the region Well, halfway between 30 degrees and 150 degrees is 90 degrees. So theta equals pi over 2 splits that region in half. So what you can do is find the area of the darker blue region to the right and then double that area. So that's what they do. The limits now, they go 2 times that dark blue area. Well, that dark blue area would be the difference between 1/2 times the integral of pi over 6 to pi over 2 of 9 sine squared theta d theta minus 1/2 the integral from pi over 6 to pi over 2 times, the 1 plus 2 sine theta sine squared theta d theta. You see, pi over 2 is usually a nice angle to have in these problems because you remember the last problem we did. The problem that we did on Tuesday, that problem we used symmetry and was able to make the integral easier to do, and that's what they're doing here. Now you don't have to use symmetry. You could just compute the area, like the area that they have here. Okay, this area here, you could just compute that area, but the calculations will be a little harder because you have like 5 pi over 6, that's 150 degrees, so you'd have to draw your reference angle and all that, and get the right value. But pi over 2 is easier. So anyway, at any rate, here we are, they use symmetry. They get this expression for the area, which is 2 times the dark blue area that you see here to the right in figure 5. And then, they just combine terms. The difference of 2 integrals is the integral of the difference. And then 2 times 1/2 is 1. And then they use the trig identity here for sine squared theta. Sine squared theta is 1/2 times 1 minus cosine 2 theta. And they work it, and they get an answer of pi. Okay, but notice they leave out steps, but I know you can fill in those steps. I know the final line here in the blue area, the yellow area I should say, where you have 3 theta minus 2 sine 2 theta plus 2 cosine theta, where theta is evaluated at pi over 2 and then pi over 6. They just say that equals pi. So they're leaving out, they know that as students you're capable of working that out and getting an answer of pi. But they leave out steps. But remember, for the final exam, I'm going to want to see those steps. So always remember, whenever you view the key to like if you're getting ready to take the test and you're reviewing and you go back and look at some old exercises and you click view key, maybe if you want to see the solutions, maybe you have trouble with one of them and you want to see the solutions, that's fine. And the view key is helpful. It guides you as to how to get to the answer. But always remember that there are steps that are left out. And for the work that you show on the final exam, I need you to put in all the steps. Okay, so just please keep that in mind. The reason I'm mentioning it is because, like on the exam 4, there was a problem where you had to differentiate a function. You had a function that you could write as a power series, and then if you differentiated the function, you would get the function, a multiple of the function that you're interested in, but then you had to differentiate the power series. But like in the key for that kind of problem, which I know I gave you in the homework, they left out details. They said, for instance, differentiating, but they didn't show the work. And some of you on your exam missed points on that problem because you didn't show out the steps, the work. So please keep that in mind. I want everybody to do well on the final. Please keep that in mind. All right. So that being said, are there any questions on this problem? All right. Very good. Very good. Well, let me stop the recording here.